Chapter 20, slides 24 to 32. Okay, so the next functional group we're going to discuss is the ester, which, if you remember in the reactivity table or chart, is very similar to carboxylic acids. They're pretty low in reactivity. You can get them to work as carbonyls, right, electrophilically, but they're not as reactive as acid chlorides or aldehydes or ketones. Very, very similar in reactivity to carboxylic acids. However, they do not have the protic system off of the oxygen, right? The oxygen I've just highlighted does not have a hydrogen on it. Therefore, esters are neutral. They are not acidic like a carboxylic acid. So this, from a reactivity perspective, alleviates a lot of the troubles we saw with carboxylic acids, where acid-base chemistry prevailed first, and then the nucleophile could do its thing on the carbonyl. In esters, we don't have to worry about that. We have about the same reactivity at the carbonyl, but we don't have to worry about that pesky acid-base chemistry occurring where deprotonation is going to ensue on the OH. Thus, esters are much more stable in many aspects, and we like to store things as esters. Because of this, we know that the proton is not going to act like an acid. And as you'll see, esters can be converted to carboxylic acid. So this is very beneficial. Esters in general are quite widespread in nature. They're responsible for many of the nice smelling aromas from flowers and perfumes and fruits. In fact, things like banana and raspberry and orange, those smells that we know of as distinctive for that fruit is the ester we're smelling. Esters also play a large role in animal biology, and as a fun example here on the right, I have a moth pheromone that's also a mating pheromone for an elephant, and I just think it's funny because I hope the moth and elephant don't coexist in nature if this is the case. But there's lots of chemistry we can do, and it's again the same stuff that we saw for carboxylic acids, but even simpler. We don't have to worry about that pesky proton being acidic. So let's take a look at some reactions. And the first one I have here is and again, it's a 1-2 substitution. So we're going to see in, up, down, out. And we're going to convert one ester to another ester. So the group that I have that's going to come off is, what makes this starting material an ester? This is an ethyl ester. And what we're going to do is run a reaction with methanol. I've just arbitrarily chosen methanol. So I want to convert the ethyl ester to the methyl ester. This is called transesterification. But notice that I have a weak electrophile, I have a very weak nucleophile. It's just partially negative, right? The oxygen is not strongly negative. So therefore, I need a little oomph, right, to catalyze this reaction. So we're first going to enhance the reactivity of the carbonyl by doing some acid-base chemistry first. And we saw this before. We're enhancing the reactivity of the carbonyl. Now it's more susceptible to nucleophilic attack. The weak nucleophile can go in and up. And just remind yourself of what you're doing here. You're exchanging one oxygen for another. These are reversible reactions. I could just as easily come back down and out and kick off the methanol I just put on. But where would that get me? Well, that would get me right back to the beginning. So that's not my intention. Right? I came on with the methanol. I want the ethanol to leave, but right now I'm under acidic conditions and it's not prone to leaving right now because I'm not going to throw out an O-, a strong base, under my strongly acidic conditions. I'm working under acidic conditions here. So I'm going to do a proton transfer first, which is just a fancy acid-base reaction where I am using Le Chatelier's principle to drive the methanol on, and I'm going to drive the ethanol off. So it looks like the proton shifted to the leaving group of my intention. But protons are everywhere, so this is just really to make me feel better about myself as I write these electron pushing steps, because in this step, I've just performed the down out. The oxygen can now come down and kick off ethanol, and now I have the methyl ester as my product. Ethanol was kicked off, and I am still protonated, technically, because I'm under acidic conditions, right? That was the proton we put in the beginning. It's still there. And so it's not going to be deprotonated until we work it up and we neutralize our conditions, because esters are neutral. So the workup is going to be under a very mild base to give me my final ester product. Right? So on with one, off with the other. These are interchangeable, which is why I have equilibrium arrows all the way through. I mean, what's to say one oxygen for another? There's one is not more stable than the other. So this is governed by Le Chatelier's principle. So if I were to start with the methyl ester and work back to the ethyl ester, my starting material, I would have to add a ton of ethanol to drive it in the other direction. So it's really just what are you putting in that drives the equilibrium in one direction over another. So these are all interchangeable. Now, esters can be converted to carboxylic acids. You have a couple choices here. You could do exactly what we just did. If you look at the bottom, you can do exactly what we just did. I'll start with a methyl ester. And we're going to exchange the O-methyl for something else. And the something else in this case is water. And what I want you to understand is that whenever you react acid and water as your reagents, this is encompassed in a broad term called hydrolysis. So whenever someone says, oh, just hydrolyze that, in your brain you're thinking, oh, they want me to add acid and water. It's a fancy term for adding acid and water. So when you hydrolyze an ester, first step, acid-base chemistry, which is exactly what we did previously. And then we're going to exchange the O-methyl group for something else, and the something else is water. The weak base, weak nucleophile, goes in and up. So we're driving the water on. We're driving the methoxy group off. It's because I'm under acidic conditions, I'm not ready to kick off O-methyl yet. It has to leave in a neutral state. So to do this, we need to do our proton transfer. So basically fancy acid-base chemistry, so that I'm not trying to shove something into the media that's highly basic. Remember, I'm driving on the water, I'm driving off what's going to be methanol. So now I can do my down, out, down, out. The oxygen can now go down and kick out the other oxygen. So I have kicked off methanol, replaced the methanol with an OH from the water, and then after workup, the product would be a carboxylic acid. Remember, carbonyls always remain protonated when they're in acidic conditions, which we started with. So I'd have to work up this reaction and pull off any excess protons. Not that I'm getting back to neutral because I've formed a carboxylic acid, but just to remove the excess protons. Another way to do this is actually to work under basic conditions, and this has a special name because of its history, and that's to do a saponification. I'll start with the same group, same ester, and instead of working under acidic conditions, I could use something like KOH, which is a strong nucleophile / base. So I'm going to replace the O-methyl with the OH, and because I'm working under basic conditions, I can skip to the chase. It's already strong, so I don't have to, enhance the reactivity of my nucleophile. I already have a negative system, negative O-, so I'm just going to do in up. I get here O-. I don't have to do proton transfers because I'm not under acidic conditions. So now I can just do the down out, right? Kicking out my methoxy group. And it's fine to let go of the methoxy group because it's O-. I've got O- floating everywhere because I added it as my reagent, so that's perfectly fine. It's gonna remain deprotonated because you just formed an acid, so it's gonna remain deprotonated until you work it up to get the proton back on to the carboxylic acid. So either way, you've made a carboxylic acid but you can do it under basic conditions, which is called saponification, or hydrolysis conditions, acid and water. The history of saponification is such that most soaps were produced from fats and oils which contained 3 ester groups. So look at the ester groups here. They're actually all connected. You can see the oxygens. So if you came in with, lye or strong base, right? You're going to exchange it with the OH-. So in, up, down, out occurs, and you've displaced and kicked off these groups, which is the glycerol, the alcohols. The soap molecule is made. So saponification was the term used to make soaps from these fats, right? And they went through the process with lye, with the strong base, to convert the esters to their carboxylate groups. And their carboxylate group, if you look, up at the top here, you can understand now that the carboxylate group is the deprotonated form of the acid that you've generated. That's very polar. And then you have the greasy carbon oily tail. That's the nonpolar hydrophobic part of the molecule. And so you can see that these head groups, all of these carboxylate groups, are what form together. And all the tails, the greasy like dissolves like, so all the greasy tails go into the middle. And that is what a micelle is. So you've got all of these molecules aligning into these bubbles. And that's what helps. The head group is dissolved in water, is soluble in the water from the outside. Whatever organic dirt you have on your hands that when you're washing goes in the middle, the greasy, oily inside. And that's what helps the water carry the dirt away, right, are these micelles. But the head group is the carboxylate that's made from that fat molecule through the process of saponification. Also, just to go back a little bit, just to talk about the usefulness of these esters, right? Aspirin is prepared from salicylic acid, which is a compound found in the bark of the willow tree. And I think I've talked with you guys about this before, right? So prostaglandins have lots of important biological functions, including stimulating inflammation and inducing fever, right? So that's what our prostaglandins do. And so they're produced in our body from arachidonic acid through a process that's catalyzed by an enzyme called cyclooxygenase. So if you look over here, you can see the carboxylic acid. Here's your carboxylic acid. And here's cyclooxygenase. And so what you'll notice is that arachidonic acid will react with cyclooxygenase in up, down, out, and the blues exchange. So you go from a carboxylic acid to an ester. Now understand what's just stated up here, right, is that the prostaglandins are produced in the body from this arachidonic acid, right, by reaction with the cyclooxygenase, and this is what induces inflammation and fever in the body. What does aspirin do? Well, aspirin cuts to the chase and says, react with me. You're basically giving the cyclooxygenase a different system, a different carbonyl to interact with. So you're pulling the cyclooxygenase to do an in, up, down, out with something else. So if cyclooxygenase is too busy over here, then there's none of this to react with the arachidonic acid. So if you're stopping the formation of prostaglandins, you stop the fever, you stop the inflammation, because you're basically busying the cyclooxygenase alcohol from doing the reaction with arachidonic acid. So this is what's kind of cool, is that this is how it works to reduce fever and inflammation, right? And what's also interesting is that over time, I don't know if you're familiar with this, but if an actual bottle of aspirin, sometimes they tell you to smell it to see if it's still good, because old bottles of aspirin, if left too long on the shelf, smell like vinegar. And vinegar is acetic acid, right? So let's draw that. What does that mean? It means that this is aspirin. If a bottle is left too long on the shelf, it undergoes hydrolysis. Then the water goes in, up, down, out. And so this whole process here, where water exchanges for the oxygen, if water exchanges for the oxygen, we're left with the leaving group, this alcohol, and the carbonyl got hydrolyzed to the acid. This is vinegar. This is acetic acid. So if over time, just moisture in the air, the bottle gets, moist or humidity in it, over time, aspirin will degrade. It'll undergo hydrolysis, and then in, up, down, out ensues, and you've basically ruined the carbonyl that does all the work. Remember, we got to keep that, we need that ester there. Well, we've broken the ester up, and acetic acid is a small molecule byproduct of this reaction. Thus, the bottle starts smelling a little acidic, like vinegar. So you want to throw the bottle away because the ester needed, for the whole purpose of how this works, is no longer present. So kind of fun, applicable chemistry. Something else, I mean, esters, again, I said wide use biologically in nature, but also in the pharmaceutical industry. And what's really interesting is here's a couple examples that I found I think are kind of fascinating. One, esters, you can leverage their properties to maybe assist the drug getting to where it needs to go. So in this first example, right, we have drugs containing hydroxyl groups are often converted to prodrugs. Prodrugs mean what you're doing is you're changing the molecule for a little while so that you can administer it, but then it's going to do something, it's going to change, it's going to do some chemistry, it's going to change into the active form later, like once digested, once it gets into your stomach, or once, so it goes in one molecule, but in your body it changes into another molecule, which is the active form of that molecule. So prodrugs are used for a variety of reasons. One of the reasons that I'm highlighting here for this prodrug for epinephrine has been developed, in which the aromatic hydroxyl group, so if you look at epinephrine, this is the active form. It's got these OH groups here, right? They're hydroxyl groups. And those hydroxyl groups are protic. So they're very polar. So what they've done is they've converted them to esters. So the prodrug of epinephrine is in the ester form. Okay, why? Well, because this very greasy T-butyl ester that they've made enables the compound to cross the non-polar membrane of your eye much more easily, because like dissolves like. So they greased it up, right, so that it can actually cross that membrane more readily. But once the drug reaches the other side of the eye, it hydrolyzes to release the active drug. So just imagine again that you've got water, hydrolysis, right? In, up, down, out occurs. This carboxylic acid is a byproduct. But you release through hydrolysis, the byproduct goes off, and then you've got the active form of epinephrine right where it needs to be to do, the important biological stuff that it needs to do. So that's an example of leveraging an ester in order to make it greasier. So property-wise, you're actually leveraging the property of the ester in order to make it cross a membrane layer. And then once it's where it needs to be, our body has tons of enzymes and water to hydrolyze esters. Here's another example. As I said, esters are responsible for a lot of the good smells that we equate to fruits and flowers. Well, sometimes a drug that you need to get administered, perhaps orally, tastes horrible. So what you can do is you can use a prodrug, ester prodrug, so that it tastes kind of nice. And then once it hits your stomach, it'll hydrolyze. Here's an example. This compound's able to dissolve in the mouth where it can interact with taste receptors, producing a highly bitter taste. So that's unfortunate. Here's the alcohol. This is a primary alcohol, right? But this is the molecule in its active form. This is the molecule we want to do its work. But kids won't drink this stuff because it tastes terrible. So to avoid this problem, the molecule is converted to an ester at the primary alcohol using this acid chloride. So what would that look like? Well, you can figure this out. The alcohol goes in, up, down, out. Notice the secondary alcohol is not touched. all happening at the primary alcohol. So in, up, down, out occurs, and it has a long greasy chain. So you just made that ester from the alcohol. And then once that drug, which actually tastes quite nice, reaches the intestines, enzymes catalyze the hydrolysis of the ester back because of that reversible reaction. Remember, we're dealing with reversible arrows, so the hydrolysis occurs in the other direction to get back to the active compound. Really cool stuff. So you can leverage esters for their smell or their flavor. You can leverage them as less reactive. You could design the ester to be greasier and thus help its properties for dissolving across a layer or getting past a lipid bilayer. So there's lots of different ways that these compounds can be used. All right, let's get back to the chemistry. So we just saw esters to carboxylic acids to esters, back and forth, esters to other esters. And we can turn an ester into an amide as well, as we've seen with carboxylic acids. And let's see, let's say I had a methyl ester. We don't need a strong nucleophile or acidic conditions. We just might need some heat in these conditions with whatever amine you are interested in using. Let's use methylamine. Because amines are already basic / nucleophilic, we just need a little heat to get over that activation barrier. So we can do in, up. We're under somewhat basic conditions. So, pushing on the amine, pushing off the oxygen. Let's do a little proton transfer here. Just so we can shove the oxygen off as a neutral species. And now we'll do our down and out. So in, up, proton shift, down, out. And the methanol was what left. So we were going to kick off the oxygen. We're driving on through Le Chatelier's principle, the nitrogen. We're here, and then we do down, out, and we've done the exchange. 1-2 substitution. Classic, right? What else can we do? Well, we can also react these esters with Grignards. Now notice the shift in arrows now. If I had a methyl ester and I reacted it with, let's say, methyl magnesium bromide as an example. This is a strong nucleophile. Remember, the carbon is negative for these Grignard reagents. So I'm putting something on that won't necessarily come back off. Carbons are not good as leaving groups. So once it goes on, in, up, I'm not going to be able to go back. I've made a very, very stable bond with the carbon. So now the oxygen can bring its electrons down, and the best leaving group is really only one choice, is the O- that I've just generated. This is a OCH3. That's now paired with magnesium, bromide. That's now a salt byproduct. And I've generated a ketone. And if you remember, ketones are more reactive than esters. So the product is more reactive than the starting material. You can't stop this train. You'd get a hot mess if you tried to do a 1-to-1 reaction. Therefore, these tend to be used in excess because you're going to get like a hodgepodge of products if you try to do a 1-to-1. Because like I just said, you've just generated, after it happens once, your product is now more reactive as a carbonyl than your starting material. So it's going to go after the product, not another equivalent of your starting material. So in these, you'll just see people write excess because there's no point in stopping the train. It just can't be stopped. You're just going to keep going. So another equivalent of the reagent does another in up. And now we have put 2 methyls on. I'm stuck now. The electrons can't come back down, so I just have to work it up. Under acidic conditions, acid-base chemistry, and I end with this. In this case, I end with this T-butanol. So I've reduced the ester, but I've also added carbons, which, you know, that's kind of cool. I started with 2 carbons. I ended with 4 carbons in the product. Very useful. Carbon-carbon chemistry. How about reduction? Well, we can do reduction as well. Notice again the arrows. If I started with a methyl ester, I'm just going to write H-, because again, I've shown you that the aluminum under these conditions loses its hydride. You know, one of the hydrogens gets released. So you're dealing with an H-, you're under strongly basic nucleophilic conditions here. So the electrons are going to attack the ester. We have in up. Notice that there's no acid-base chemistry that occurs because it's an ester, not a carboxylic acid. So it's not tempted to do that. Simplifies my mechanism a little bit here. I'm just going to cheat and just avoid. The O- is very likely going to attack the aluminum again and kick out another hydride for further use. Remember, lithium aluminum hydride is really 4 equivalents of H-, because the oxygen will keep attacking the aluminum and kicking out more of the H- because the aluminum oxygen bonds are pretty strong. So the electrons can come off, or sorry, the tetrahedral intermediate here is going to collapse and do a down out. Right, here's your O- that got pushed off. This is where another release can occur, right? The oxygen can attack the aluminum and another H- can be released. So just to show you, we could say the aluminum gets attacked again, and then it releases another H-. So there's tons of H-, even one molecule of lithium aluminum hydride is really 4 H- that can get released into the system. Take a look at what you've just formed. You've formed an aldehyde. Very reactive, second most reactive. We started with an ester. There's 4 H- floating around. Who's most likely to get attacked? Well, the aldehyde. So this train does not stop. You do not isolate the aldehyde in these reactions because you've got H- floating all over the place, and your product is more reactive than your starting material. So it just keeps going. It's a train you can't stop. Very similar to the Grignard. Now the O- is stuck up on the oxygen. It can't come back down. So there's nothing left for us to do other than work it up under acidic conditions. And we end up with the alcohol, ethanol in this case. We didn't add any carbons. We started with 2 carbons. We ended with 2 carbons. I don't have to draw the hydrogens in. They're assumed to be there, but I did add those 2 hydrogens in. So that's the reduction of an ester all the way down to the alcohol, down the reduction ladder. I reduce the number of carbon-oxygen bonds and increase the number of carbon-hydrogen bonds. Okay, the last reaction I want to cover is, are we like doomed to never form the aldehyde? I want to understand if there's a way. I mean, aldehydes are functional groups in their own right. Is there a way I could do a reduction but just stop at the aldehyde and not have it over reduce all the way down to the alcohol, kind of like the double reduction? And there is a way, but I can't do it with this reagent. So there's a classic reagent that we use called DIBAL, which is a special aluminum hydride, and I'll draw it out for you, and you can, look at the difference between them. So lithium aluminum hydride, let's just remember what that looks like. It's aluminum with 4 hydrogens surrounding it. 4 bonds on aluminum makes the aluminum negative, and its counter ion is lithium, so it's a salt, and it has 4 H- available. DIBAL stands for di-isobutyl aluminum hydride. And it looks like this. Notice that it only has 3 bonds, so it's not charged. It has 1 hydrogen, 1 hydride on it, and the other 2 groups are carbon groups. They're isobutyl groups. So we could just say that they're R, right? I can just call them R. Okay? All right, so what happens? Well, aluminum is not, in a state where it needs to shove the hydride off, right? So in order for this reaction to occur, the first step, and I'm just going to write RRH. The first step is Lewis acid, Lewis base reaction, where the oxygen, which we've seen the oxygen of the carbonyl act as the base, but there's no proton here. We have a metal. The aluminum is very susceptible to oxygen bonding. Aluminum oxygen bonds are quite strong. And so the aluminum and oxygen are attracted to each other, and the aluminum accepts the electrons from the oxygen, and the oxygen donates its electrons, but it's not an SN2. It just forms that 4th bond on the aluminum. The aluminum is now negatively charged, and the carbonyl is now positively charged. So what you've just done is you've enhanced the reactivity of the electrophile. You've now heightened the reactivity of the aluminum, because the aluminum's like, oh no, I gotta do something. I gotta get rid of one of these bonds. And the weakest bond is the one to the hydrogen, the hydride. So it releases the hydride, but what's there to catch it? The hydrogen leaves and goes, wait, there's a carbonyl right here. I'm gonna go to this partially positive carbon. And then the pi bond breaks. So the first step is acid-base chemistry to sort of get everything heightened and activated, both for the reagent and the carbonyl. Once in that form, this high energy intermediate collapses to do the in-up. And this is where it stays. Notice now the oxygen is satisfied. It's no longer positive. The hydride was added to our system. Right, here's the hydride. It's now reduced to that carbonyl carbon. The aluminum only has 3 bonds. It lost the hydrogen, so now it's happy. So it's actually a stable aluminum alkoxide. It's stable. That's the key. It's going to sit right here, and they typically are water soluble because of the oxygens. And so it's going to sit like this until you work it up. The workup here is probably the most important workup we've seen thus far, because the reaction isn't over until you put the workup in. The workup is actually not acid-base chemistry. The workup is aqueous, so water, with these tartrate salts. So what this is a bunch of OR minuses. You're adding aqueous base of the oxygen minus variety. And what that does, technically, it's reversible. You're trying to, did you ever have a dog that was like, had your shoe in its mouth, and you're like, okay, I gotta get the shoe out of the dog's mouth, right? In this case, the dog is the aluminum and the shoe is the oxygen. Because what do we want? We want these electrons to come back down and that group to be released, right? This is a substitution at the end of the day. I want that group to be gone. I'm trying to replace it with the hydrogen. So in order for the dog to let go of the oxygen so that my tetrahedral intermediate can collapse to give me back my carbonyl, I need to entice it with something else. So this is you saying, hey, aluminum, here, if I give you this oxygen, let go of the other one. So you're kind of doing an SN2 at the same time that you're doing the down out, the down out part of the reaction. But in order for down out to happen, the aluminum has to take something on that it wants, and oxygen for an oxygen exchange is good. So what you're doing is you inundate, using Le Chatelier's principle, you inundate your aqueous media with OR minuses, these tartrate salts, and over maybe 24 hours, you hope that the aluminum will exchange. But understand that once it does, the collapse ensues. And you're left with an aldehyde. You've killed the reagent. There is no more aluminum. There is no more aluminum hydride left. All of those are gone, quenched by your workup step. So the workup step is not only releasing this bond so that the tetrahedral intermediate can collapse, it's also reacting with any of the aluminum starting material that you might have and basically killing that from going forward anyway. So the workup is where the release occurs. And thus you end on your desired aldehyde. FYI, when I was a student, DIBAL, the AL stands for the aluminum, but I always used to think that because aldehydes end in al, that your DIBAL is like aldehyde, you would end in the aldehyde. That was like my quick and dirty way of remembering this. This is the one that stops at the aldehyde, the dibaldehyde reaction. That was just my way of remembering.